start off by explaining or just emphasizing the upcoming due dates. So measures of dispersion, we'll finish that today. We just have one more question as far as the class notes go. And that homework, the corresponding homework, will be due tomorrow, of course, at midnight. And the quiz for measures of central tendency and measures of dispersion together, that quiz will be due on the 28th. I believe that is Sunday. Yes, so that'll be Sunday. So those are the two assignments for this coming week. With normal distributions, that'll be next week. So far, I have it due for the 30th, and we'll see how far I can get with that section. But that should be a deadline that should stand. Besides for that, again, no workbook assignment this week. I already went into my math lab and just gave everybody 10 out of 10 for workbook 6, I called it. So, so just the homework and the quiz. That's all you have to worry about this week for this class. Does anyone have any questions before we pick up where we left off? Yes?
Workbook 4 was page 15 and 16, and 5 was 17?
Workbook 5 is 15 through 17.
15 through 17, okay.
Mm-hmm. And then workbook 6 is just some, that's just what I labeled the free points that I gave everybody. So if you see workbook 6, you should have a 10 out of 10 because I gave everybody a 10 out of 10. So besides for that, let's go ahead and get started. So we'll pick up where we left off. So we finished example 5 right at the end of class, and so example 6 is still in the theme of talking about not only just the measure of central tendency, but this additional idea that we add on called the measure of dispersion. Remember, the measure of central tendency tells you what the center reasonably looks like, either using the mean or the median. And then the dispersion, mainly the standard deviation, is a way to measure how compact or dispersed the data is from the mean. A small standard deviation means the data is really close to the mean. A larger standard deviation means that the data is a lot more spread out and diverse. So let's look at example 6 here. Professor Hall, no relation to me, is performing a statistical analysis on the final grades for some class and wants to find out what percentage of his students lie within 2 standard deviations of the mean. So to start this problem off, there's a data set. And naturally, with a data set, this normally encourages the use of technology. And this is further supported by them first asking for the mean and the standard deviation, which we can go ahead and quickly find out. So go ahead and take out your calculators. Let's go ahead and figure this one out right fast. And you should have, it seems to be 10 data values. So it should be pretty simple stuff so far. The mean and the standard deviation are found using the same exact command in the calculator. So we click on second mode to quit out of this. We click on stat and move over to calculate, C-A-L-C. Finally, one variable statistics, just like we did last time and the time before. So I'll kind of breeze through this part. So the mean is 86. And just as a reminder, I'll put X with the bar on top because that's what the symbolism means. And the standard deviation is, remember, that's SX in the calculator. They went to the nearest 1,000. That's 3 decimal places. That's 7.38. So far so good. This is assuming I typed in everything correctly. Can someone confirm you got those numbers? I'm going to assume what I typed in is good. If you did not get this, just be very careful about how you typed everything into the calculator. You might have typed in 85, you might have typed in 75. Many different things happen. Okay. So steps not 1 and 2, technically it's A and B. The value 2 standard deviations below the mean. So 2 standard deviations below the mean. So we talked about this a little bit before when we started off the section. We're going to go a little bit more in depth about how to find this here. So below the mean, well, we need the mean. And we found that to be 86. So below the mean, that implies we need to subtract from the mean. And, well, if we need 2 standard deviations below the mean, then that means that, well, the standard deviation is 7.38. What's that?
Well, we do the 738 times 2.
That's right, times 2, because we need to subtract from the mean twice to get 2 standard deviations from the mean. So that's where the 2 is coming from here. So we have to subtract by 2, or in other words, we are subtracting the standard deviation 2 times. And whatever this comes out to be, I think that it's some interesting number. 86 minus 7.38 times 2. 71.21. I rounded to 2 decimal places. I just realized that. I rounded to 2 decimal places. Why did I do that? 379. That's for the thousandth. Okay, sorry about that. That's 3 decimal places. So, as mentioned, human error happens all the time. I do it all the time. So let's slightly erase that, because in the eyes of my math lab, they will consider that completely wrong. So, so let's make sure that's 379. Cool. So 379 times 2. There we go. So let's try that again. 86 minus 7.379 times 2. So slightly different answer. Again, to my math lab, they definitely want you to be specific about this. 71.242. All right, so hopefully that seems good. So far so good. And then in part D, they want 2 standard deviations above the mean. Very similar process. We just use a plus sign instead of a minus sign, because we want to go above the mean. So we're adding, but still 2 standard deviations. So 1 standard deviation is 7.379, and then times 2, because we're applying this twice. And whatever that value is, 86 plus 7.379 times 2. 100.758. So this gives us an interval of 2 standard deviations from the mean. The interval being, well, the lower bound of the interval being 71.242, and the upper bound representing 100.758. So it gives us an interval. And then part E, looking at the scores, exactly how many of Professor Hall's students have grades that fall between the 2 values?
All 10.
Yeah, all 10. Simple as that, all 10 of them. So remember, 71.242 is the lower bound, 100.758 is the upper bound. How many of those values fall within that interval? All of them. The 85s, the 95s, the 75s, those are all within that interval. So that's exactly 10. There's 10 of them. And then part F just says this is exactly what % of the total number. Well, It's just 100%. It's 100%. Here they're asking for the percent and not the proportion. So that's 100%. 10 out of 10 people scored within 2 standard deviations of the mean. So that concludes this problem. So it's a fairly straightforward problem, I think. Does anyone have any questions before we move on? If not, I did want to give some motivation for the next section because we are done with this section in terms of the notes. The standard deviation, it gives us an idea about the generalized distribution of a data set, as we've been talking about. And so you'll find that in the real world, and if you take statistics next semester, you'll see a lot of graphs that look like this. Now you can model graphs like that using these rough bell-shaped, curvature. And when you are able to use a model to roughly approximate a normal distribution like this, then you get some really neat properties from this. These properties are going to be what we talk about in the next section. But there's a lot of phenomenon that occur in biology, in economics, and academics that follow this normal distribution. It's a very, very common distribution. And if your data correlates with that, then you get a lot of very helpful ideas from that. A bunch of assumptions you seemingly get for free. These assumptions, 68% of the data will lie 1 standard deviation from the mean. About 95% is 2 from the mean. And 99.7 is 3 standard deviations from the mean. This is the important idea, and I'm going to emphasize this in the next section, but that's the assumptions you get. It gives you an idea about how the proportions are distributed and how the standard deviations help you determine that. It gives you an idea of what percentage of values lie within a number of standard deviations from the mean. So with the conclusion of this section does imply the necessity to complete the corresponding homework, which, as mentioned, is due tomorrow. So that gives you tonight to just let it, to let your brain soak up the information, and then tomorrow to probably start the homework at 10 p.m. and finish it by hopefully 11:59. Just don't email me at that time. But if you email me before 8, of course, I'll answer. And if you need to schedule any office hours, that the whole thing. So let's go ahead and move on to normal distributions. So normal distributions, this will be the last idea going into the Unit 3 assessment, which I'll talk more about next week. Again, workbook assignment. If you missed my email or my announcement in class last time, there's no workbook assignment this week. I just gave you free points. So don't worry about it. So let's move straight into what a normal distribution is. Now, I kind of mentioned it above already. A normal distribution is a type of distribution where the data tends to be around a central value with no bias left or right. And if you want to think about a shape of this, the diagram here at the bottom of the screen, try to get both of these in the screen at the same time. There we go. You can visualize that spread at the bottom, that shape, that's going to be what the data tends to resemble, where most of the values stay close to the center and then are less and less frequent as you move away from the center in a symmetric way. Generally, grades for classes resemble this. You get a lot of C grades, you get less B and D grades, and even less A and F grades. And so this spread has this bell shape to it. So academics follows this all the time. And generally, if you have a bimodal distribution, which is where there's two humps, that's normally indicative of cheating. So it's a very interesting way for teachers to quickly see what's going on with the class. So some of the assumptions that we get for free with a normal distribution: a bell-shaped appearance, the mean, median, and mode are all equal. Okay, that's convenient. So there's no point in finding any one of these separate. We expect to see a symmetric shape around the center. It's the same thing on the left and same thing on the right. And you also expect, with the symmetry, this is kind of a corollary idea to the aforementioned one, 50% of the data is to the left of the mean and 50% is to the right. Because if the center is right smack in the middle, 50% on the left, 50% on the right. I guess your right is this way and your left is this way. So these are the expectations that we get for free. So this is why it's pretty nice for us to get as close to a normal distribution as possible. We get a lot of assumptions for free, and it gives us a very concise manner of analyzing a data set. Now, one of the more important ideas, now in this class we call it the 68, 95, 99.7 rule. In statistics we call it the empirical rule. So if you hear me call it the empirical rule, it's the same thing. Empirical rule means the same exact thing. But in any case, it's just it's a shorthand that's used to ultimately remember how the standard deviations associate with the proportionality of data in a distribution. And as I mentioned at the end of the previous section, just a moment ago, one standard deviation from the mean is going to hold about 68% of the data. Two standard deviations, about 95% of the data. Three standard deviations, 99.7. This is just something you have to memorize. But there is this nice graph here that you can utilize, and I'll be coming back to this graph to explain how these percentages will be interpreted if they give us certain values, and how to interpret this this graph. Because there might be some interesting symbolism here. You might notice there's Greek letters spread out, and it really translates quite nicely. You'll just have to see for yourself that it's not as bad as it looks. So we'll talk about how to interpret this graph as we work through some of these problems. And again, it says at the bottom, 68% lies within one standard deviation. 95 is 2. 99.7 is 3. So let's look at some problems and see how to interpret a situation like this, how to use this information. Okay, so we're going to scroll down to example 1 here. There's a doctor who finds patients' heart rates are normally distributed and figures out some information regarding that. So he says that the average is 65. That's going to be helpful. Standard deviation is 7. So the ideas from the previous two sections also occur in this section. In fact, we need a mean and a standard deviation to even have a normal curve in essence. So everything is based off of the previous sections. And then what they'll have you do in the homework for a question like this, they want you to label the x-axis. So notice it says A, B, C, D, E, F, G. So they want you to label that axis. Now, there's one value we can put definitively. What value is that, and where does it go?
65.
What's that?
65.
Where does that go? Which letter?
B.
Yeah.
Right.
So D is right smack in the middle. That is always a definitive value. That is 65. So, so the center, we get that one for free. Now the standard deviation of 7 will help us look at values adjacent to this one. So how would we figure out, say, E?
Seven.
What's that?
I don't know.
How would we figure
I
out?
think it's seven.
Well, standard deviation doesn't tell us the value explicitly, but it does tell us how to reach that value in relation to the mean.
Add 7 to 65.
Yeah, it's 7 to 65. Because we're going one standard deviation above the mean. So 65 is the middle. Yeah, you go one standard deviation above the mean. So that'd be 65 plus 7. That's one standard deviation above, which is 72. And so the next one,
79.
what's that?
It's 79.
It's 79 because we're now 2 standard deviations above. So same thing as before, but times 2 because we're 2 standard deviations above. So that's 79. And I'm guessing you can see what the last one is. 65 plus 7 times 3. Because 3 standard deviations above. And that seems to be, yes, 86. And we can do the same thing in the converse direction.
Well, we subtracting, right?
Yeah, we subtract. So pretty much it's the same computations reflected, and we just subtract. 65 minus 7, 65 minus 7 times 2, and 65 minus 7 times 3. Because this is 1, 2, 3 standard deviations from the mean, respectively. So what is that? So 58, 51, and what's that? 44. 4 plus 7 is 51, plus 7 is that. And if I messed up my math, just let me know. I think that's right. Provided my simple mental math is correct, that would conclude this problem. That's all it asks us to do, is to construct, well, really not even to construct the graph, just label the tick marks, as they're called. And so that's it. It's based off of starting with the mean in the middle, and then working your way outside the mean using the standard deviation in this appropriate manner. So one way we can interpret this is that about 68% of patients in this problem have a heart rate between 58 and 72. Because 58 and 72 are 1 standard deviation from the mean in either direction, and 1 standard deviation corresponds to 68% of the data. So that's sort of the interpretation of this, as we'll talk about a little bit later, or throughout the section, rather. Does anyone have any questions before I move on? Okay, let's go ahead and look at the next example. Okay, so this is an example about people buying a car. So if you ever go on Kelley Blue Book and look up prices of a car, they do have a somewhat normal distribution of car prices. And it doesn't look as nice as this one as far as I could find, but it is something that does explain the distributions. And so here they have the prices of a new car, and it's normally distributed. So they're pretty much taking the information that was above, so the information up here, and writing down just some concise information about it. So they're giving you this chart in the problem. They tell us that the mean is 18,000, which makes sense because 18 is right in the middle, and it's in thousands. So 18 is right in the middle, and the standard deviation is 2,000. So it makes sense that we're going in increments of 2,000 in both directions. So I think it's good to understand how the construction of this chart of this graph represents what we know about labeling the x-axis. And so we can use the 68, 95, 99.7 rule to determine what percentage of people paid any certain amount for a car. And we'll start off with part A, less than 14,000. So let's see how to use a graph like this. Now 14,000 is right here. I think we can all see that, it's right there. If we want to visualize the region that we want to know about, less than 14,000 would be this region that I'm shading in black right now. So that's what we want to figure out the percentage of. Now the 14, let's see, if we follow the 14, it seems to have something to do with this 95%. But on the other side, it comes down here. So what the 95% tells us is that's the percent of this part right here. That's what this tells us, that this is 95% of the data right here in blue. But we don't want that. We want this part right here, that little slither of information right there. So we have 95, but we want that part. So what's something we can try and do? Anyone have any intuition? So you wouldn't do that. It looks very tempting. It's very tempting to do that. The only problem with that is the 99.7 does not, the 99.7 stops right there, and there's a little bit more right after it. So not 99.7, but from really 100%. So really, so we want to figure out this region right here. So by subtracting one, well, really we could look at it either way. 100% minus 95% is 5%. I think we can all agree on that. What does this tell us if we were to illustrate this? So let's erase some of these details that I have right here. So we said 95% was this part here. The 5% that we just found tells us the complete opposite of the blue region. So everything that's not the blue region. So I'll contrast it with a nice red. So the 5% tells us, well, everything that's not blue is this region and this region on the right. Because that's also included. I mean, we don't want to know it, but we got it anyways. That is the extra 5% that's not in that blue shaded region. So this region plus that region is 5%. But we don't want that much information. We only want this right here. So how do we figure out that region?
Would it just be half of 5%?
It's half of 5%. We want half. It gave us twice as much information that we needed. So we have to turn around and say 5% divided by 2, which is 2.5%. And that is part A. And that will tell us exactly this region right here. I am now shading in black. So we're going to do another one like this in case that might have seemed a little bit odd of a process. Does anyone have any questions so far? Again, part B is going to be fairly similar. If not, let's go ahead and look at part B now. So I'm going to go ahead and erase everything. So part B, more than 20,000. Okay, where's 20,000 at? Right here. 20,000 is right there. We want more than 20,000. So more than 20,000 think we can all agree that it's referring to this region over here. So that's what we want. We want to figure out the percentage of that region. Well, if we were to scale up that 20,000, so let's erase that circle. So if we look at the 20,000, I'll do this in blue, it seems to go up, and it has something to do with 68%. So now that's the number we're looking at now, because that's what's touching the 20,000. And the 68% also goes down here and touches the 16. So the 68% is referring to this little region right here. So this is 68% of the data. But we don't care for the in-between part of the data. We want what's on the outside, because that's where our black region is at. So we don't want the 68%, we want everything else. So
100% minus 68%?
yeah, 100% minus 68%. Because we want not what's in between, but what's outside. So in other words, we're finding the complement using kind of a familiar word, but in a slightly more ambiguous nature. The complement just meaning the opposite. So what this tells us, well, one, it tells us it's 32%, but the 32% is not the final answer, because the 32% also gave us this other side, because this is also not in the blue region. So we have to include it by virtue of the complement. So these two regions together give us 32, but guess what? We have to figure out half of the information. We only care about this one over here. And this is perfectly symmetric. So now we have to take the 32, and guess what? Divide by 2, just like we did in the last problem. 32 divided by 2 is 16. And so 2.5 answered part A, and 16 answers part B. That's an idea for how we utilize a chart like this. Does anyone have any questions so far? Because when I taught this my first semester, everyone made me stop and explain this all again. So I want to make sure, and that was 2 years ago, but just want to make sure everyone's up to speed. If not, let's look at another one and see if that might help you out. But first, we need to describe something that is very important. If you take, and you find me mentioning this quite a bit, if you take statistics next semester, the z-score comes up more than pretty much anything else. So the z-score refers to, it sounds a little technical, but it's how many standard deviations a data item is above or below the mean. So if you have a z-score of 3, positive 3, that means you're 3 standard deviations above the mean. You can also have a negative z-score, or standard deviation couldn't be negative, but z-scores can be negative. So you can have a z-score of -2, and that means you are 2 standard deviations below the mean. That's how this is interpreted. And there's a formula for determining this. The z-score is you take a data item, you subtract by the mean, and then you divide by the standard deviation. So in this class, if I were to take everybody's ages, I could find the mean of everybody's ages, guessing it would be 19 or 20, and the standard deviation, which would probably be maybe 2. But every individual person would have a corresponding z-score. So every data value has a z-score. So if I found your age, whatever that age may be, that age can be converted to a z-score. And then you may have a different z-score, you may have a different z-score. It just depends on whatever that number is. So every raw data value has a corresponding z-score. And z-scores are very helpful. Again, we do talk a lot about z-scores in statistics. They're a very important idea. A negative z-score means you're below the mean. So you can have a negative z-score, and exactly what it means is that you are, or this object represents a value below the mean. Positive z-score, above the mean. So if you are, say, older than the average age in the class, then you would have a positive z-score. And if you're below the mean, then you would have a negative z-score, despite the fact that age is a positive number. Z-scores are very helpful because they tell you, well, what your displacement is from the mean. And for a lot of statisticians, they care a lot more about that than what the raw values represent. Now, if you're working backwards, say if you know the z-score already, or if you know the number of standard deviations, in other words, away from the mean, and you want to figure out the raw data value, so basically working backwards, you could do a little bit of algebra, but you would ultimately get this formula for the data item. So these are both the same formula. It's just one of them is worked out algebraically to where you solve for the data item. Since a lot of people don't really like algebra too much, I figured I would just go ahead and complete the algebra here. So let's talk about how these two scores may be applied. So example 3 says a set of data items is normally distributed, which means we're allowed to use the z-score stuff. So that's just a formality. With a mean of 150, okay, that's helpful, that's concrete, and a standard deviation of 20. Again, that's very helpful. And then it just straight up tells us, convert 210, just the number 210, to a z-score. Okay, so this is just making sure we can apply the formula correctly. So as I mentioned, every single data value has a corresponding z-score. Normally the way I notate this is a z with a little 210 next to it. And this is a fancy way, so 210 is a subscript. It just means that the z-score that corresponds to 210 is equal to, and it's a tiny 210, it's to the bottom right of the variable. Now the formula tells us exactly that we start off with the data value, which is 210. We subtract off the mean, which they told us was 150. And then we divide by the standard deviation, which they told us was 20. Okay, well, that's pretty easy. 210 minus 150 seems to be 60. And you can do this in one step. It doesn't really matter. But 3. Now, if you put this, I do want to preface this. I've seen this a few times with students. It's one of those calculator PIMDAS problems. If you put this in the calculator, like the way I'm putting it, yeah, if you put it in like this, you're not going to get the right answer. The calculator doesn't understand that the 210's in your numerator. It doesn't have that intuition like we do as humans. It's a dumb calculator, so it only knows what we tell it. So instead, you can either just do the numerator by itself, then divide, or if you use parentheses, you can do it all at once. So I've seen that happen a few times. Not a mistake, but you're rushing through a test. You may have the right answer and type it in the calculator incorrectly. So you might just want to be aware of this, just in case. It's better you see it now, though, instead of on the test and get docked a few points for it. Okay, so 3 is the final answer though. And what this tells us is that 210, the number 210, the raw data value 210, is 3 standard deviations above the mean. 3 standard deviations because that's the number, and above the mean because it's a positive number. That's how we interpret this. Does anyone have any questions before we look at something fairly similar? If not, let's look at example 4. Okay, they tell us the mean is 100. Again, very helpful, in the standard deviation of 10. Find the number of standard deviations each given measurement is from the mean. Well, they changed the wording on us, but the number of standard deviations from the mean is the z-score. It's the same thing. It's asking you to find the z-score, in other words. Now, the way they worded it, there is one caveat to this, and it seems as though I did not put an example here. I might have to add a third one to really emphasize this. But let's just go through the first two. So they're basically wanting us to find the z-score, because the z-score is the number of standard deviations from the mean. So the z-score, let's try it again. The z-score for 137 is, well, you take 137, you subtract by the mean, which is 100, you divide by 10, and from here we get, well, 137 minus 100 is 37, divided by 10 is 3.7. So 137 would be 3.7 standard deviations above the mean. You can have decimal standard deviation. It doesn't have to be whole numbers. You can have fractional standard deviations. In fact, when you look at realistic data, these types of standard deviations are more common. Problem 2, same idea, just different value. The z-score for 112.6. 112.6 minus 100 divided by 10. It's the same formula. I just replaced 137 with 112.6. Now that's 12.6 divided by 10, which is 1.26, I believe. Because you move the decimal place over once. Let's just make sure. 0.6 minus 100. Oh wait, it should be, yep, I'm glad I checked. Or was that right? I don't know. Let's find out. 1.26, I don't remember what I had before. Whatever I had, this is what I should have. I can't remember what I just read. 12.61. Okay. So that tells us we are 112.6 would be 1.26 standard deviations above the mean. Now I'm surprised I didn't choose an example that resembles the next thing I'm going to write down. I'm going to throw in an extra example. Try to throw it down here. And I want to pick 90. I'm going to pick 90. Now there's a specific reason why I'm choosing 90. So again, we would work it out the exact same way. Minus 100 divided by 10. And so that's negative 10 divided by 10, which is negative 1. But negative 1 is not the answer. Because the problem, the way they word it, it's kind of sneaky, is how many standard deviations are you from the mean? They're asking about standard deviation. And standard deviation cannot be negative. The z-score and the standard deviation are very much closely associated, but the way negative 1 is interpreted, the way we interpret negative 1 in our minds as a z-score is that you are 1 standard deviation below the mean, because the negative tells us below. So really, this is one standard deviation below the mean. So notice how the -1 became a +1 by virtue of our interpretation. So 1 would be the right answer when they word it in this way. So kind of an interesting thing, but I wanted everyone to be aware of that in case you did get an example like that. Because standard deviation, again, cannot be negative. So it's really, we're looking at the magnitude of the z-score. And magnitude just means there's a negative, just get rid of it. For absolute value, in other words. Okay, any questions up to this point? If not, let's look at example 5. All right, they tell us a mean. They tell us a standard deviation. What is the score that is 2 standard deviations above the mean? So notice they're not asking for the number of standard deviations. They're not asking for a z-score either. Here, score just means score on a test. What they're doing is, well, they're giving us the opposite information. 2 standard deviations above the mean. What does that tell us? Does anyone happen to see what explicitly that tells us? In mathematical symbolism.
We multiply something by 2?
Just something equals something. That's all I'm looking for right now. Just how do we translate that to symbols? Or if you have a verbal explanation for it, but nothing computational yet, just an equivalency that this is telling us. It tells us a z-score. That tells us that z, because z is closely associated with the number of standard deviations from the mean, what does that tell us z is?
130.
So it's going to be, what's it going to be? Just 2. 2 standard deviations above the mean. Well, standard deviations, anything involving above or below the mean refers to the z-score. And 2 standard deviations above means we have a +2. So that's what we're told. The z-score is 2, and now we need to find the raw data value that corresponds to 2. So basically, what value would give us a z-score of 2? So we're working backwards to find the raw data value. So we're using the second formula here. We're trying to figure out the data value given the z-score. Or in other words, if your plus gives n standard deviations above the mean and minus gives n standard deviations below the mean. It's a very equivalent thing. So the data item, I'll follow the formula exactly, is equal to, what starts off with whatever the mean is. The mean's 100. We are 2 standard deviations above the mean, so we're adding 2 times the standard deviation of 15. Wait a minute, this looks oddly familiar. This looks very familiar, what I just wrote. Yeah, I've seen this before. Have any of you seen this before? Let's see, 2 standard deviations above the mean. We've done that. It's a formula of intuition. Notice we've taken our intuition and we've quantified it in a formulaic manner. So perhaps that association may be beneficial in some way. So in any case, it's a very quick formula. 2 times 15 is 30, 100 plus 30 is 130. So this would be the value that corresponds to a z-score of positive 2. And a z-score of positive 2 corresponds to 2 standard deviations above the mean. That's how this sequence of association works. Let's look at another one. 2.5 standard deviations below the mean. All right, you all get a chance to redeem yourselves. What does this tell us?
He is 2.5.
No,
No.
no. You're close.
So negative.
It's negative 2.5, yeah. So I was wanting someone to say the positive version to just let everyone know that we have to negate it because we are below the mean. So notice standard deviation is not a negative value, but standard deviation combined with the phrase below, that comes together as a z-score that is negative. The standard deviation tells us the magnitude. So we're looking for the data item that is 2.5 standard deviations below the mean. It doesn't make sense to say negative 2.5 standard deviations. So the mean is 100. Again, I'm following the formula from right up here. The z-score we found, or in other words, we are below. The z-score, or the standard deviation, so however you look at it, is 2.5 times whatever the standard deviation is. Or, well, that is the standard deviation. Whatever the, well, okay, the standard deviation of 15, in other words, the one that they gave us. So I'm pretty sure 2.5 times 15, so that's 30 plus 7.5, 37.5. 1 minus that, I don't know, 61.5 or something. Let's find out. 100 minus 2.5 times 50. 62.5, I was off. Okay. 62.5. Again, very easy computation. And that's already the answer. So what that says is that the raw data value, so the raw data values, when I say that, that's referring to scores on a test. So what it's saying is that if a student, or there's a boundary that's a score on a test that's 62.5, and this would be 2.5 standard deviations below the mean. And so if we interpret that with the 68, 95, 99.7 rule, the middle 95% of the data, let's see, 68, 95, 99.7, so 68, 95, that's 2 standard deviations. 62.5 is outside of 2 standard deviations, which means it's not part of the inner 95% of the data. In statistics, we call that unusual. Anything that has a less than 5% probability of occurring. But again, this is prerequisite stuff for a future class that you might or might not have to take. But it's fairly interesting, I think. Does anyone have any questions about this one before we move on? If not, let's look at example 6. Women's heights average about 64 inches, standard deviation of 2.3 inches. And we're going to use the 68, 95, 99.7 rule, so that graph that we introduced in the very beginning, to determine the typical ranges of women's heights. In what range will approximately the middle 95% of women's heights lie? So normally they call a typical range as 2 standard deviations from the mean. But they do tell us this in an implicit manner. They're asking for the range, so they want two values. They want the lower part and the upper part that encapsulates the inner 95%. And so they want us to find out those two values. So the middle 95%. So let's scroll up a little bit. Let's go to that chart. Not that one, but this one. They're asking about something involving 95%, and that tells us two standard deviations. What is this connected to? It's connected to that thing, and it's connected to that thing. Now, all you need to worry about is the -2 and the +2. It's two standard deviations below the mean, two standard deviations above the mean. And this is a visual representation. You can also consider you don't have to use a visual representation. Normally it's more helpful when you're trying to find percentages given the standard deviations, but that is one way in which it can help. You can also realize that the middle 95%, well, the middle 68% is one standard deviation. The middle 95% is two standard deviations. So two standard deviations below and above the mean. So we need to figure out two standard deviations below the mean, two standard deviations above the mean. And that will give us an interval of the middle 95%. And we have to know, so you have to know that 68 corresponds to one standard deviation, 95 corresponds to two standard deviations, and 99.7 refers to 3. So you have to know that. So let's start off with 2 below the mean. So how do we figure out the value that is 2 standard deviations below the mean? Well, what do we need to take away? Or in other words, what do we need to start off with in order to take something away from it?
64.
Yeah, the 64. We need a mean in order to look beneath it or below it. And if we look beneath it, we're subtracting to go underneath the 64. Well, what's the value of our increments? It's the 2.3 standard deviation, which they tell us in the problem. But we're not doing that just one time. We're doing that 2 times. So 64 minus 2.3 times 2. It's 59.4. That is the lower bound of the middle 95%. And if we want 2 standard deviations above the mean, we just add. We start off with the mean. In order to look above, we have to add. 2.3 is the standard deviation, and we have to do that twice. So this is the interval. So there's 2 answers here. That's the interval of values, the range of values. So this means that, according to this example, women's heights are expected or will typically lie in between 59.4 inches to 68.6 inches. This would be the typical range. And this is based off of the center. So heights and weights of individuals, just in general, so this is biological, that's generally normally distributed. Does anyone have any questions about example 6 before we look at example 7? Okay, let's move on to example 7. So in some classes, so not in this class, but in some classes, teachers will grade using a curve. Now, if you ever go to a graduate program, they tend to do this a lot more than not, because you're kind of competing with your classmates in a sense. So some people grade using a curve, and they're assuming that the grades are normally distributed, which means, cool, we can use z-scores and stuff. So that's, again, a formality. The first thing of interest to us, the average grade is 70. So in other words, the center, the central tendency, and they tell us the standard deviation. Find the test scores for each grade interval using this rubric that we have here. So what this is saying, so let's start off with what makes a grade an A. A grade is an A grade if the z-score for that grade is greater than 2. So that means we need to find the score that corresponds to a standard deviation or a z-score of 2, because we need to know what's larger than that value. So what we need to do, so we're trying to figure out the data item given the z-score. So we're given the z-score already. So the item, I'll just call it item just to save a little bit of space on the screen here. The item is equal to, so we're already given the z-score, so we're not using the z-score formula where it's all by itself. We're going to use the data item formula, which says we start off with the mean. And since we have a positive z-score, this means that we are looking at 2 standard deviations because the z-score is 2. And since the z-score is positive, this is 2 standard deviations above the mean. So we're adding, well, the standard deviation is 7, and we're doing that twice. Again, if you put 7 times 2 or 2 times 7, same thing. So it's just 70 plus 7 times 2. So that's 70 plus 14, that's 84. So to get an A, you need above an 84. That's what we just found. Or I guess to make this a little bit more concrete, I'll use a variable x because I'm going to be using a few compound inequalities later on. So above an 84. Okay, so the next one, what about to get a B? Well, we know what the upper bound of getting a B is. It's an 84, because once you get to that range, or once you hit 84, you go to the next one. So if anything, we already know the upper bound. Now, if you do get an 84, I don't think the problem really, I don't remember any equal to signs in this problem, but it's not going to ask you anything specific. It'll just have just blanks and you'd put 84 in the next one. So we know the upper bound of B, because if you're above 84, then you're an A grade. So now we need to figure out the lower bound. So we're going to look at, so we did A, now let's look at B. So with this one here, we know what the upper bound is, so we already figured out that part. Now we need to figure out the other side, when z is greater than 1. So this means we need to figure out what happens when we have a z-score of 1. So we need to figure out the item. Top one was z is equal to 2. Next one, z is equal to 1. So the item, still 70, plus, well, the standard deviation is 7, but we are only looking at one standard deviation above the mean. One standard deviation because z is 1, and above the mean because 1 is positive. That's why we're adding here. And so that's 77. So that tells us the lower bound. So between an 84 and a 77, that's the B grade. Didn't really change anything. That's just a nitpick of mine. No worries. Means the same thing. Okay, so that's the B grade. Now we move on to the C grade. Well, we know what the upper bound of the C grade is, 77. Because once you're above 77, you're in the B range. So what about the lower bound of C? What's the lowest grade you can make to get a C? So let's look at C, and we want to figure out the lower bound. So in other words, when Z is -1, remember, Z score can be negative. In fact, that tells us some useful information. Since the Z score is negative, this means that we are below the mean. So that means we want to put a minus sign here. The standard deviation is 7, and the magnitude of the Z score is 1. So that's 63. And the reason why we use minus is because we have a negative Z score, which means we are looking at standard deviations below the mean. All right, let's move on to what it takes to get a D in the class. This would be Z is equal to -2, because what we want to look at is this association. Well, we know the upper bound for a D grade, it's a 63, because if you're above a 63, you're in the C range. So again, we have a Z score of -2, a mean of 70, minus 7 times 2. We use the minus because the Z score is negative, which means we are below the mean. And the Z score, the magnitude of the Z score is 2, which tells us how many standard deviations below the mean we are. So that's just 70 minus 14, which is 56. And luckily for us, this already answers part E here. I mean, if you are not in the D range, if you're lower than the D range, you're in the F range. So it's, if you get any score less than 56, there's nothing really to solve here. The lowest grade to make a D, if you get lower than that, it's an F grade. So notice how this changes the conventional 10-point grading scale. So an 85 or higher would definitely get you an A. Some C grades are now considered B grades, and so on and so forth. There's it changes the 10-point grading scale. There's one more idea I want to introduce. It's a fairly simple idea regarding a percentile. So when you took the ACT or the SAT, I think it's mainly the ACT people around here take, you don't only get a composite score and a whatever other scores they give you. I can't remember, but they will also give you a percentile. And that pretty much means the percent of people that you scored better than. That's what a percentile is. If you scored in the Well, if you scored in the 25th percentile, that means you did better than 25% of the people who took the test. So it gives you an idea of how you scored relatively compared to other people. Now, example 8 is kind of a challenge problem in a sense, but if you get this right, we can get out a little early. A score in the 75th percentile is the blank, since 75% of the data is less than this data item. As soon as you get this, we can wrap it up for the day. Score in the 75th percentile is the blank, because 75% of the data is less than this item. Yes?
Third quartile?
Yes, the third quartile. The third quartile, because remember the increments, how they go from the minimum to the first quartile, or yeah, from the minimum to the first quartile, that's 25%. From the first one to the median, that's another 25. And from the median to the third quartile, that's another 25. 75%. Okay, well, that wraps up the notes, but I want to ask you all how we should utilize the next class session, because I am now officially 1 day ahead. I have one free day now, and I can utilize this day in any way I choose. So I'm trying to think about, should we do a review session on Tuesday and then not have class on Thursday? Should Tuesday be a review session or a homework session? I'll stay here. I won't have any new notes, but you can come by if you have homework questions. Or we just don't have class on Tuesday and have the review session on Thursday. Or Monday. What day is it? Yeah, it's Wednesday, sorry. So yeah, Monday and Wednesday. So what's the consensus here?
What was it again?
Ask for a review on Monday, no class on Wednesday.
Because we can do a review on Monday and then no class on Wednesday, and it's just an early spring break. I could sit in here on Wednesday or, be around Wednesday in my office if anyone has any questions. Let's think on that. We'll just get it over with on Monday. I'll answer any questions after class on Monday for this homework. And then we won't have class next Wednesday. So you could focus on your assessment or do whatever the heck you want to do. All right, good? Cool. All right. If you didn't sign the roll sheet, make sure you do so. Other than that, I'll see you all on Monday.